If you ask a computer for a random number, you can get a pretty random number, but there's something absolute about it. Like, if you rewind this video, you'll get the same random number over and over again. Not so random if you know what will happen for sure. In fact, the only reason computers are useful is because they aren't random. We've controlled the tiny pieces of hardware to send electrical signals that are processed into the screen that does exactly what you want. Except for the times when your computer is running slower than you want, you get the spinny wheel of death and things start crashing, but that's kind of besides the point for computers. They do exactly as they're instructed to. In the code, at least. Whether it does what you want is a whole other problem. So what do we want computers to do? One potent tool they offer is simulations, where we can recreate blood flow, protein folding, and a nicely rendered COVID-19 virus inside a computer. Truly remarkable stuff, but to get these incredible models, we need some science. And a notable question to ask might be how far down in scale can we model? And if we can find the building blocks that lie beneath the secrets of the universe and we perfectly simulate it, can we predict the future? Now in practice, predicting the future is quite impossible. In fact, we don't really have a model that can exactly pinpoint where tiny particles are and where they will go simultaneously. But I'm not much of a scientist. Instead, I might ask if you took two boxes of the exact same stuff in the exact same position moving in the exact same way at this instant, would they continue being the same or would they diverge in their actions? And here lies an origin of determinism, the idea that the state of the present uniquely determines a singular future. So how well does this idea hold up? Mathematically, this may seem sound at first, but maybe it doesn't quite hold up. You see, if we think of a particle as having a position, we could represent it as a function over time. The velocity would be its derivative, and the status of every higher order derivative would be the same, at least in this initial state. So you might think this means each of the derivatives must be the same and you get the same function of positions, but that's not quite true. If we wanted a function where each derivative at 0 was 0, we would be able to take the 0 function as well as the function e to the negative 1 over x squared with the whole at 0 filled in. I mean, each derivative of 0 is just 0. That's quite trivial, but for e to the negative 1 over x squared, we need to take limits for an e to the negative 1 over x squared term multiplied by the sum of some negative powers of x. Read the annoying math computations or just believe me. It's boring enough, but not seriously hard to prove if you consider any power of x times e to the negative 1 over x squared will result in terms that are sums of similar terms, each of which goes to 0. Of course, there will be an entire class of functions with this property, not to mention you can splice a bunch of different functions together into more endless possibilities, so there may very well be multiple outcomes with the same initial starting state. That being said, determinism doesn't come in one size, so maybe it isn't right to use this mathematical approach at all, and a philosophical one is more appropriate. Moreover, you can pick different models or scales to apply these ideas. Maybe you believe in determinism on a larger scale, that specific hardships in your life are what lead you to become the person you are today. Maybe it's simply the memories you carry, the genetics you're born with. Maybe it's some higher fate or destiny known by God or some powerful mechanism of the world, waiting to be carried out. But regardless of what you believe, what matters is that you continue forward, choosing the path that makes your life better, whether it be scientific, philosophical, mathematical, or simply practical.